Last week we talked about machines and frames, and hopefully you guys have a good feeling for that. I gave you a couple extra days to work on the homework. So I guess we'll start off. Are there any questions on anything related to frames or machines? Feel 100% comfortable with those? So, okay. Well, we're going to do. So we're going to talk about friction today briefly. There's a lot we could talk about with friction, but I just want to touch on some highlights. And then, as you may have noticed, the final homework is posted, and that has to deal with machines, and I think it's frames and machines only. But I didn't. There is a homework on friction, but I'm not collecting it, and so it's actually posted, and I'll post the solutions to it. But they might even be integrated in the assignment itself, but I'll have to check. But that assignment is actually under the week 9 materials. So if you go into the modules and you look under week 9, you should see assignment 9. And that's just the friction assignment. I'd encourage you to look at it though, because friction will be part of the final. And so the depth at which I go into it in the class probably won't be covered in the final. So for example, belts and pulleys, the friction on belts, usually we don't cover that on the final. It's a little extraneous, but it is interesting. It's only a short piece, so I put that in there at the end. Wedges, I'll probably know more when we're going to meet today and talk about the final. So I'll give you more of an idea of that when we have our final review. So the plan is right now is you'll have your quiz on Wednesday, machines. I won't be here tomorrow, so I won't have office hours the normal 1 to 3 time on Tuesday. So I've moved those to Wednesday, which is will work because the homework is not due until Friday. And then next week's quiz will be friction, and that'll be the last quiz. And then, as I was saying, we'll have a final review, which will be to be announced in terms of the date and the time. But I'd like to do that on probably the end of dead week, since our final is already on Monday of finals week. And at that point, I'll have more information for you as to what to expect on the final. So what I can say about the final, though, is it'll be weighted more towards chapter 6 and 5 and 9 and 8. So the stuff that you haven't been tested on. Oops. All right. So I do want to talk about general friction and do a couple of examples, mainly because I want you to understand the basics of it. And there's more, obviously, information in my lectures than I'll be able to cover here. But a lot of this is based on the stuff that you did in Physics 144 if you took it here at Poly. And it's just an extension of that. Generally, the thing with friction that's a little different than what you used to with the other subjects is that you have potential motion in different directions. So in the past, everything would be static. Here, we're looking at something that's just on the cusp of motion. So we call it impending motion. And so a lot of our problems, we can assume that friction is equal to mu times n, coefficient of friction times the normal force. But remember that relationship is only good for maximum friction. So that tells you the maximum friction that's available in your system. But just because you have a force applied to something doesn't mean that the friction is going to be that. So as you may recall, friction is it pushes back as much as it receives. So if you push on a box on the floor, the friction is going to push back the same amount. And so if you put 1 Newton on a box, 1 Newton of friction is going to push back 2 Newtons, and so forth, until you reach the maximum static friction, in which case you'll overpower and the box will begin to slide. And as you recall, or you'll see in my lectures, is that kinetic friction is lower than static friction. So it's easier to keep something moving than it is to start it. All right. So I want to talk about an example on an incline real quick, just and let's see. So let's do this. Okay, so now there is a relationship that says that if I have an object sitting on an incline like this, and I have an angle here, theta, then if I want to know at what point, if I put this object on here and I raise it, at some point it's going to slide. And it turns out that when it's going to slide is independent of mass, because as you can imagine, mass makes normal force proportional to friction. And so it turns out that as you raise this up, if you want to determine the angle at which it's going to slide, it's just the tangent of that angle equals mu static. Or if you take the inverse tangent of mu static, you get that angle. And so this can be derived very easily, but and you've probably seen it in physics, but it bears out, it holds experimentally, and it's probably it's like a high school physics experiment where you take different objects and different coefficients of friction, and you try to see how much you can raise this before it slides. So based on the idea, though, not necessarily the angle, but the idea that in this system, if as we raise it, we know that the friction is always facing this way. So we know that our object's always going to slide down the incline because gravity is the only force acting on it, besides friction force, which is related to gravity, the gravitational. So what we do, imagine now we apply a load to it. So I'm going to redraw this. And we still have our object. Only now we're going to apply P. All right. So let's say that's 15 degrees, and we'll make this 20 degrees. And we'll say that here's our object, our box. So box equals 500 newtons. And we're given that P equals 150 newtons. And we're given that mu static is 0.35. So knowing all that, we want to know what will happen. So will box go up, stay put, or slide down? So that's our quandary. So how do we solve that? What do we do? Well, with anything, we can treat this as a particle. So when we make our free body diagram, what we can do is we can tilt the axis. And what we're going to do is we're going to say that in our new reference, there's E, but because I've tilted the axis, we add those, and this now becomes 35 degrees. And we know that so we don't know whether friction is going uphill or downhill. So I'm gonna assume that friction is pointing this way. And I'll find out if I'm wrong or not. And then I know that I have a normal force points up on my y-axis. And the last thing I know is I have gravity or mass mg. So I know that's going to be the 20 degrees here, and that's just going to be the 500 newtons. And so P is still 150. So just like we've done before, we're going to sum the forces. So we'll start with sum the forces of the y to 0. And so if we do that, we have, excuse me. Yeah, sorry. We have n minus 500 cosine 20 degrees minus 150 sine 35 degrees. So we can solve for n. N equals 556. And so from this, we can calculate our friction force max. And that's going to just equal to 0.35 times 556. And so our friction force max to about 194.6. Okay. Now we're going to look at if we sum the forces in the x. Now, so we know this is the maximum friction force. So what this tells us is that because the thing about this problem that makes it a little more, not this part, but the part I'm going to talk about is that because P, if you vary P, that's going to because pushing the object into the incline, and therefore that's going to change your normal force. So if we, let's go ahead and sum the forces in the x, 0. And if we say, with that one, we're going to have 150 cosine 20 degrees, I'm sorry, cosine 35 degrees. All right. And then, so if we're assuming friction is going down and this is going, so we're going to say that's negative. And then we're going to say plus 500 sine 20 equals 0. So what we're going to find then is, and let's look at this and see what we get. So this is where it gets a little interesting. So I'm going to go ahead and calculate it right now. So this part of it's so this is 122.8, and so we know that's going down the hill. And then the 500 sine 20 is the P that's going up. So, oh no, I'm sorry. This is, oh, I apologize. This is not sine, no, this is the, sorry, I got that backwards. So this is 122.8 that is going to be pushing up the ramp. So where we say this value is 122.8 pushing up the ramp. This is the 171 newtons that wants to go down the ramp. And so this is where kind of the comparison comes in, because what we found now is that there's 171 newtons that wants to go down the ramp. There's 122.8 that's pushing it up the ramp. but we know that we have as much as 194.6 newtons available. So what that means basically is that if we add this plus this minus friction force equals 0, then friction force is about 48.1 newtons. And so now if we were to draw this, if we were to draw this, what it would look like is you would have your you would effectively have, you'd have 122.8 from, that would be the P input, and then you'd have a value of 48.1 of friction, and then the value going down would be 171. And because the friction max hasn't been seen, then the object's just going to sit there. So we know that the now, granted that when we know, so what we're saying is that this F max of 194.6, that's whether it's sliding up the hill or down the hill. That's the maximum friction. And so because we haven't exceeded that with this amount, it means our object's standing still. All right, so it's kind of like a forced balance in a sense. And so that's why I did this, is because it's a little different than what you've been doing. And I want to make sure that you understood. Now, the next step to this, though, which is interesting, is what if you wanted to figure out what is the P value, so that you're just, I guess, the maximum P value. So I guess the idea would be, what P value would you have to apply in order to make the object move? And so you could do a bunch of iterations if you wanted to, and the reason why you'd have to do iterations is because as you increase P, that also increases the normal force. So if we take it to the next step and we say P value to cause motion. So how high a P value do you need in order to go up the hill? All right. So this one, given the amount of time we have, I don't want to do the whole derivation, but it's really what it comes down to, and I can just show you how I did it. And this isn't something I'd ask you on a quiz or anything, but it's just kind of an interesting. So if you assume up, just slipping, meaning we're going to just go up the ramp, then the way you solve this is you first set up this first equation, which is friction force plus, and this is just summing the forces in the x. So you have friction force going down because you're assuming it's slipping up. And then you have W sine 20 and then P cosine 35. Then you do the same thing, sum the forces in the y, and you solve, and you get normal force is equal to P sine 35 plus W cosine 20. But you know at slippage, friction force is equal to mu static times N. And so since you know N, then what you can do is you can substitute this here with mu static times N. So if I rewrite equation 1, I have mu static N plus W sine 20 minus P cosine 35. So I just took that equation. And then, but I know what N is. So because equation 2 is N, I can substitute in for this what N is. And now all I have is P. And so I'm keeping my weight of 500. My angles are the same because, of course, if those change, everything else is going to change. And then what that does is it allows me to isolate P, and then I go through the steps. This is just a simplification of it. And I end up with about 542 newtons, or exactly 542.458. It keeps going. So this tells me then that if I apply this much load, that it'll move. And what it's saying is that as you apply the P, as I said before, is just you apply P, the normal force isn't increasing at the same rate that the upward that the force to push it up the ramp is. So the normal force increment is smaller as you increase P than the force to push it up the ramp. So eventually you're going to reach that. Any questions? So, I mean, we could do stuff like this, but I think the takeaway here is the idea that in a lot of friction problems, you start off with an equation in the X, an equation in the Y, and you'll notice that generally the equation in the X includes this friction force value. The equation in the Y often includes N, but we know that we can equate these just by this equation, right? Because we know friction force is mu static N. And so and since most of the problems are going to be just impending motion, you can use this relationship to go between the X and the Y. And that's what allows you to solve a lot of these. Okay. All right, so and what I should have done is I didn't pin that. So whoever was watching that on video isn't going to be able to see what the hell I did. I apologize for that. Let's see, let's go back to, okay, so here's an example. We have a beam and it's sitting, so you have this 10-foot beam, weighs 1,200 pounds. You want to move it to the left onto a platform. And so you have a force P pushing on this dolly. So thing to think about is when they don't give you information, for example, you assume that the rollers on the dolly on the bottom are frictionless. You also assume that the mass of the dolly is negligible. But a lot of times, even if you didn't assume that, it won't matter in the problem because, again, you're not really moving. You're just impending motion. So you're just about to move. And so it really doesn't interfere with the problem. But so if we look at this 10-foot beam, way to think about it is we have this beam, and let's go ahead and go back to this. So there's our beam. Now we know that we have normal force at A, and we have got normal force at P, and we have friction at A and friction at D. Now the reason we've drawn it that way is because remember that we have something like this where we have a cart. So we're pushing the cart this way, and then here we have it sitting up on a ramp. So the idea is if we push the cart this way, what's going to happen? And this is again where you get the two situations. Either the whole thing, the cart and this beam, are going to slide onto the corner here, onto the ledge, or this cart is just going to slide underneath the beam. So one beam slides on ledge, or two cart slides under beam. So those are two situations. So So we have, this is all we have for our free body diagram. We know that the center is 1,200 pounds, so it's uniform. And we're given, based on the distances, we are given that, let's see, it's 8 feet. This is 8 feet between these 2 points, and this is 5 feet between these 2 points. So what we can do is, let's first figure out what these normal forces are. So if we sum the moments about A to 0, then we know the normal force at D times 8 minus 1,200 times 5 equals 0. Do the complex math, we get ND equals 750. Therefore, we know NA has to be 450. So we get a total of 1,200. So now we know those normal forces. Now, so the next, so you imagine, so what now? What do we do? Well, if you think about it, we're really looking for max friction. And the other thing to think about too is that when they said that in the problem statement says that the dolly is higher than the platform. Okay, it's higher. So what does that mean? If it's higher than the platform, then if we draw the beam, it's going to look kind of like this. If this is the ledge, then then what are we going to have? The beam is going to sit in an exaggerated manner. It's going to sit like this. Now that's massively exaggerated because the dolly is like up here. But my point is because it's sitting slightly higher, instead of it all being along the surface, because you probably noticed that it was sitting on part of the actual wall, or the ledge that it was sitting on was X 2 feet. So it was actually sitting, this is 2 feet. But if it's sitting up in here, then we can assume that all of the normal force is all focused on that one corner point. Okay. So that's why we're able to do that. So now we just want to think of what is the max friction. So F at A, max. So the friction, that's what is the maximum friction here. Okay. Well, what's that going to be? Well, we're given that mu static is equal to 0.3. All right. So we know that it's just going to be what? 0.3 times the normal force at A, right? Which was 450. So we can say that it's basically 0.3 times 450, which is just equal to 135 newtons. All right. And then we look at the friction B max. And what's that? Well, we know it's 750. So 0.3 times NB, or 0.3 times 750. And that gives us 225. All right. So again, let's draw what this looks like. So we have, here's our beam, and we have this under here, applying force there, and then this is sitting like this, right? So we know that the friction is, and so we know the friction is actually on this corner and on that corner, right? Because that's how it's sitting, like I drew here in an exaggerated way. So we know that the friction here is pushing back 225, and the friction here is pushing back at 135. So if it's going to move, we know that P is going to equal 135 or greater than or equal to. You know, and you can just say P equals 135. We're not going to split hairs on it. Greater than, sorry. The alligator eats the bigger meal. Even after all these years, sometimes I mix up my greater thans. So I have to go back to first grade and say the alligator eats the bigger meal. So P is greater than or equal to 135. And so we can see that because it's going to either push here or it's going to slide here. And so obviously it's going to slide where the lower force is. So mathematically, this is a very easy problem. But the reason I show it to you is because conceptually, I want you to see, start thinking about these friction problems, about how do you actually approach them? And they're not difficult math-wise. And as you've seen throughout statics, as compared to the other classes you guys take, the math in this class is really easy. But it's the concepts and understanding the application that's challenging. So anyway, any questions on this? Does that make sense? All right, good. All right, let's look at the next problem. We just call them problems like they're a bad thing. We should call them fun challenges or something. Exciting morning rituals. How about that? Okay. Here's another example. This one looks a little more complicated, but so ignoring the pulley, really what we're looking at here is what is the mass, the range of masses required for this thing to stay in equilibrium. So if the mass is too low, it's going to slide down the hill. If the mass is too big, it's going to move up the hill. So we essentially want to know what is the range that we can put there. So these types of problems, you're going to have a lot of fun in dynamics. It seems like they're obsessed with at least the first few weeks, obsessed with pulleys where you release one and you calculate the acceleration of the other on all kinds of inclines. So, but just to give you an idea, it's coming down the pike. All right. So there's our drawing. So we know incline is 0.3. We have the drawing. So what I've done, let me label this really quick. Kilograms, V static equals 0.3. And voila. Okay. So there's what it looks like. All right. Now, so if we look at the pulley, again, with pulleys, if you just cut a line through them, we can see that the weight or mass is equal to 3 times the tension, because there's 1, 2, 3 tensions. Now, when we come up here, we have the single tension, but we find that because of the way the pulley is, these 2 tensions are going to be. So we're going to solve for T. And in this, knowing what these relationships are, and then that'll allow us to determine what this is. So first thing, of course, is free body diagram. So we can draw. Let's see, I guess I'll just draw the object instead of the point. So you have the normal force of A. You have 2T. And so we can point the arrow like this. So if it's going to slide up, then mu static N is going that way. If it's going to slide down, then it's still mu static N, but it's going that way. And then, of course, we know we have 100 pounds going down. All right. So let's first figure out slide. So let's say slide down ramp. So this is if we're going to slide down the ramp. So There we go, it's a little better. So we know that if we sum forces in the x, 0, and again our x being the incline, we get 2t minus mu static n, because we're assuming the friction force is a maximum, and then minus 100 sine 25 degrees. All right. So so that equals 0. So we need to know what n is, so we can, and so n is going to be the same regardless if we're sliding up and down. So if we sum the forces in the y to 0, we get the normal force of A is just simply equal to W cosine 25 degrees. So we know that NA is equal to 90.6 pounds. All right. So we got that, have that. So now we can plug that into here and we can solve, and we get T equals 7.54 pounds. All right. So if tension isn't at least 7.54 pounds, then it's going to slide down the ramp. So let's do the same thing. Slide up, slide up ramp. So in that case, we have same thing, only now same force, or same equation, sum the force x and 0. The only difference is it's 2t instead of slide down. Oh, I apologize about that. You guys probably saw it. I was looking at the next line. This should have been a plus. This is correct, but this should have been a plus because I was looking at my notes. I'm surprised someone didn't interject and tell me I was wrong. I really did that just to see if you were paying attention. No, I was reading my notes. So yeah, this was plus because tension's going the opposite direction. All right, so now in this one, it's the other side, right? Because if we're sliding down the ramp like this, then tension and friction are both going the same direction. Now they're going the opposite direction. So same thing, 2t mu static n. We know that that's, mu static is 0.3. That's 90.6. I know you guys can plug that in. Minus 100 sine 25 equals 0. So now we get a t equal to 34.7 pounds. And so the nice thing is now that we have t, we know from up here from our relationship with the pulley that 3t is equal to the weight. So that just means that we have 3 times 7.54, so slide down. And that's going to equal 22.6 pounds. And slide up, and that's just going to be 3 times 34.7, right? So it's going to be either this or this, and that's going to give us a value of about 104.2 pounds. So now we know that essentially 22.6 is less than or equal to MB, which is less than or equal to 104.2. So that's the one thing about this, in here we always talk about pounds as pound force. We don't deal with pound mass. So as soon as we're in the English system, you don't have to worry about gravity. Make sense? Any questions? All right. So hopefully you're seeing kind of a pattern here, the way these problems work. The idea is, again, is to use the relationship of friction and friction as a maximum with the normal force. So really this equation, friction force max equals mu static n. That's really the key to all of these problems in their various forms. All right. So let's, there's one, I had a couple more, but let's do this problem here since we can finish it in the time that we're here. this one looks more complicated than it is. But again, that's what I want. You know, some of these problems are actually fairly straightforward, and I want you to get used to just not being intimidated by them. Just look at them for what they are, not make them more than they need to be. So give you a chance to read that real quick. So ask yourself, how are we going to solve that? So what I would say is, before I show you anything, go ahead and make the effort to draw the free body diagram for each of those. So you're gonna draw the cylinder as one free body and the mass, the block, of another. So take the time to try to do that, and then you can compare it to what I got. Okay, so let's look at this. Let's see, static under C. 0.4. Okay, so hopefully you got something that looks like this. You want to draw each one separately, and even though they're touching. So we know that there's a normal force between each of them because they're pushed against one another. We know that for the block, it weighs 3 kilograms. The idea is that if this moment is turning here, it wants to push to the right. So the friction is going to oppose that. You have a normal force here, static friction 0.5. And then over here, you have the same thing. The only thing is, if this wants to spin, then the friction is going to oppose that, okay? And then you have the weight, and the normal force points up. So you have two situations here. You can move block, or you can spin disc, right? So if this object was immovable, then what would happen? This would just sit and spin, kind of like you're barbecuing your tires to impress people.
That's a quick question.
So you sit there and this spins around like this, but if it's not, then it's just going to push this over. So we really want to compare the friction force to this, which really is fairly straightforward, because we know that weight,
Professor.
normal force of B.
Professor.
And so
My mic working.
we know that normal force of B is going to be 3 times 9.8, or basically about 29.4 newtons. So therefore, friction max is going to equal half of that, 0.5 times 29.4, and we get 14.7 newtons, okay? So we're trying to push this to 14. So if we can generate more friction than 14.7, then this block's going to move. So we just do the same thing over here, where we have 6. We know that the weight is equal to 58.8 newtons. That's 6 times 9.8. And so F max is equal to 0.4 times 58.8, which is going to be bigger than, it's going to be 23.5. So what will happen is, since this has, so we have 23.5 newtons here of friction force, that's the maximum. So if this, as long as this object is less than that, then it's going to push the object. If the object ends up creating more friction, so if the object created 24 newtons of friction, then this wouldn't move, it would just sit and spin. Now, we're not talking about motion ever, we're just talking about the impending. So before it would move this wouldn't move, this would start to slide, but that's as far as we go, because friction's different in motion than it is in static, and you'll learn that in dynamics. Okay, that's about all we have time for. I hope this was beneficial to you guys. Again, I'll be in office hours today, 10 to 12, and then Wednesday. And so have a good rest of your day, and thanks for coming in.
Professor, is my mic working
Thank
now?
you, so.
Hello?
Professor, can you hear us?